If you're ready. Perfect. It's my great pleasure to introduce Professor David Blecher from the University of Houston, who will speak on von Neumann conditional expectations and non-commutative representing measures. Please.
Thank you very much. Can you all hear me?
Sure.
Yes.
Okay, so for some reason my Apple Pencil is not working. Let me just try to connect it. That should be working now. So, but it seems like okay. Can you guys see that?
No, we don't see a screen.
No, we see your bicycle and a tent.
Now see you.
Okay, let me try that again. Yeah, I guess we should enjoy the distractions because the rest of it is going to be just slides, right?
All right, there you go.
How is that?
Yeah,
okay,
fine.
so may I begin?
Yeah, we can see your slides, but we can barely hear you.
Oh, okay. Let me turn up the volume.
Yeah,
It's fine now.
Okay. If there's anything wrong with the volume, please tell me and I'll change my earbuds. Okay, so just for the abstract, I'm more or less going to begin. I'm going to say a few preparatory things, but then we will talk about the theory of normal conditional expectations on von Neumann algebras, describing some new contributions to this theory, such as a correspondence between conditional expectations and non-commutative weight functions affiliated with the centralizer. And then we will, inspired by Arvison's Hardy space theory, we are going to talk about a new kind of non-commutative representing measures of non-commutative characters on operator algebras or non-commutative function algebras. And then the last part of the talk, we will consider and give successively more general solutions to the problem of the existence of representing measures in the weak star case. That is, when do there exist weak star continuous positive extensions of non-commutative characters? And this is joint work with my friend Louis, and it should be appearing soon in AIM. So just by way of introduction, if you think about classical functional algebras, which are subalgebras of commutative C-star algebras, in the classical books, for example, Gamlin, about the first thing you look at is the maximal ideal space, which is equivalently the set of scalar-valued homomorphisms, also known as the characters. And you go on to show that the Gelfand transform is an isometric homomorphism from the algebra to the maximal ideal space. You can define the spectrum in terms of these characters. And then you discuss the Choquet and Shilov boundaries, peak sets and peak points, generalized Hardy algebras and Hardy spaces, generalized analytic functions, Gleason parts, etc. And you can find that in Gamlin's book or or there are several other texts on the subject, like Stout's book. So key to this theory is, and we've heard this mentioned several times in these in this week, are representing measures, which for a character, it's a positive measure on the space on which the function algebra is living, satisfying this formula here that the character is integration against mu. But in functional analytic terms, of course, a representing measure is a positive extension of a character to a state on the containing C-star algebra. Then so in the theory of generalized Hardy spaces that I already mentioned, that you can find in Gamelin's book or Stout, etc., you start with a representing measure for a particular character, define H infinity to be the weak star closure of your algebra in L infinity. And similarly, you can define HP as the closure in the LP space. So everything is defined in terms of this character. You can call this the primary character. For example, if A is the disk algebra or H infinity of the disk, then this character is evaluation at 0. And well, we've met this in many talks already this week. For example, Raphael's talk, he went through this in great detail and some generalizations of this. The important representing measure is Lebesgue integration on the circle, which of course is a state and is a weak star continuous state on L infinity. So the picture is like that. Yeah. So if in addition A is what is known as a Dirichlet or log modular algebra, or more generally a weak star closed Dirichlet algebra, then it turns out that these Hardy spaces above behave very similarly to the classical Hardy spaces of the disk, and you get all these great theorems that we know and love. And these generalizations are due to Hoffmann, Halson, Laudenslager, and many other people. So to summarize, at the heart of the function theory from the 50s and 60s is this weak star continuous character and the weak star continuous positive state extension, which corresponds to this representing measure. Now, more generally, in the case of a character in a weak star continuous extension, the classical Hoffmann-Rossi theorem proves the existence in general of normal or absolutely continuous representing measures. So the theorem says that weak star continuous characters of a function algebra, so A is contained in L infinity, which I'm calling M, have weak star continuous positive state extensions to M. Such extensions, and Raphael illustrated this in several examples in his talk, and other people have mentioned this as well, correspond to representing measures which are absolutely continuous with respect to mu. So there's a comment here. This should be related to the Henkin measures in Raphael's talk. There should be some good connections between this general Hoffmann-Rossi situation that need to be explored. So because this will actually, I guess what I'm about to display is kind of at the guts. It's kind of at the guts of what of the very abstract and general things that come later. But these abstract general things have the following thing embedded in its guts. That it's still there. I'll give a proof that uses an ancient idea of Saracen and Koenig for a related result. So this is the Hoffmann-Rossi theorem. Again, weak star continuous characters have weak star continuous positive state extensions. So we can actually fit the proof into one slide. So first of all, because it's your character's weak star continuous, it is realized by integration against some L1 function. This L1 function need not be positive or have the right norm, but we're going to fix that. You write this function R as a product of two L2 functions. Let J be the kernel of phi, define E and F to be the closure in the L2 norm. So this is the key that we are using Hilbert space arguments to prove a function theoretic result. And then for F and J, it's easy to check that, well, by definition, that's equal to that, which is obviously equal to this, which is bigger than 1 over c squared for some constant, because why? Because F is in J, so it gets killed, and you get 1, and that's by the formula above, that's equal to 1 minus FR, which is, we know that R is AB. So that's equal to that, which is less than equal to that constant. So that gives you the inequality above. You can see from this that A is not in F, so E is not in F. So you can choose the unit vector H in the ortho complement. You can check that the integral of F H squared is that inner product, which is 0, because F is in J, and so HF is in EJ, which is contained in F. And since A is simply a sum of J, and we've checked what happens on J, and it's obvious what happens on here, it follows that this integral is a normal state on M extending phi, and that is the end of the proof. This is probably the only proof I'm going to do in this talk, but I did it for the reasons I mentioned. At the end of the 1960s, Hoffmann generalized the theory of generalized Hardy spaces and its weak star continuous character approach to a von Neumann algebraic setting. And so I'm going to go through this part quite quickly, I think. It's really just motivational. In Hoffmann's setting, he has a very special weak star closed subalgebra of von Neumann algebra. And the primary character, so Hoffmann was trying to generalize this work from the 1950s that I mentioned in the first part due to Halson, Laudenslager, etc., Hoffmann. So in Hoffmann's case, you have this primary character replaced by a weak star continuous homomorphism phi from the algebra A onto a von Neumann subalgebra. So this is a von Neumann subalgebra. And we're going to call such a homomorphism a D character below. And with this in mind, we define a non-commutative representing measure, or an absolutely non-commutative representing measure, to be a normal or weak star continuous conditional expectation. And I'll define conditional expectation in a moment. Psi from M to D, including phi. So the simplest example is the upper triangular matrices, which lives between the two von Neumann algebras Mn and the diagonal Dn. And the canonical conditional expectation, of course, is the trace preserving non-commutative representing measure, which extends the canonical D character on A. Sorry, I'm not sure if I said that right, but I think that it's pretty clear what's going on. We have there's a conditional expectation E that on the upper triangular matrices just restricts to the it restricts an element in the upper triangular matrix to the diagonal, and that is a homomorphism. So it's a D character. So it's good to keep this example in mind. Okay. Are there any questions? Yeah, it's unfortunately I don't have another device open so that I can see you guys. So it's like I'm giving a talk into thin air. So, but feel free to interrupt. if you have any questions. Okay, so a conditional expectation. I mentioned that word in this talk. They'll usually be normal, that is weak star continuous, unital, positive, or equivalently contractive, idempotent, D-module map from a unital C-star algebra onto unital C-star subalgebra. Of course, for if you say normal, we're assuming that these are actually von Neumann algebras. And in this talk, we are going to simultaneously generalize important aspects of the theory of conditional expectations of von Neumann algebras and the theory of representing measures. So yeah, so it's important to realize that this is a simultaneous generalization. That's one of the points. And in doing so, we're going to make some new contributions to the theory of conditional expectations of von Neumann algebras. So let me describe this theory of conditional expectations and its motivation from probability theory. If you're only interested in non-commutative representing measures and not von Neumann algebra theory, feel free to zone out, but just remember the forthcoming main point of this section, which is that conditional expectations on von Neumann algebras are not monolithic. They're not blocks of stone that you can't peer into. They can be classified, parameterized, are responsive to the tools and treatment of analysis. Okay, so let's just motivate from probability theory. So we're going to state the things from probability theory that probably everybody knows, and then we're going to generalize them to von Neumann algebras. So if K a mu is a probability measure space, then it's well known that von Neumann subalgebras of L infinity correspond up to null sets to certain subalgebras, sub-sigma algebras B of A. And for any such subalgebra D, there's a unique conditional expectation E from M to D satisfying this key equation. That's the key conditional expectation equation. Also, this unique expectation is normal and faithful. So faithful, you all know what faithful means. And we will call it in this talk the weight-preserving conditional expectation. It might be better to call it in this setting the probabilistic, but I'm not going to use the word probabilistic because in the later setting, we won't necessarily have states. We might have weights on von Neumann algebras, and weights correspond to general measures, not necessarily probability measures. Okay, so if we write this weight-preserving conditional expectation as E mu, then, so this is the key point, that any other normal conditional expectation is given by this formula. It's just E mu applied to Hx for a density function, H, whose expectation with respect to the probabilistic expectation is 1. And such H is sometimes called a weight function. So the takeaway is that you can study all conditional expectations in terms of weight functions, and also, of course, you need the one fixed probabilistic conditional expectation. So you can use tools in the treatment of analysis on these weight functions. A final thing that could be said is that any other, or this all normal conditional expectation, assuming that it is faithful, it is the probabilistic conditional expectation, or the weight preserving conditional expectation for another probability measure, which in retrospect is the obvious one induced by a mu and the conditional expectation. And we are going to show that a similar structure pertains in the non-commutative case. So the basic text on non-commutative integration theory is Takasakis Volume 2, beautiful, beautiful book. So a weight is a zero infinity valued linear functional on the positive part of the von Neumann algebra. So the thing to bear in mind is that weights are non-commutative integrals. Why are weights non-commutative integrals? Because the canonical example of a weight is the integral on L infinity of x plus. We say that the weight is semi-finite. So you'll remember the term semi-finite from measure theory. Turns out that there's several competing definitions of being semi-finite for weights, but we'll take the definition as there's an increasing to one, which is finite with respect to the weight. And a beautiful fact, so this is a very foundational fact, is that every von Neumann has a faithful normal semi-finite, which we will write as FNS weight. And because of this, this is one motivation to regard von Neumann algebras as non-commutative measure spaces, because von Neumann algebras are non-commutative infinity spaces. But if you fix one of these FNS weights that we know always exist, we can view this pair as a non-commutative measure space. Okay, now let's talk about conditional expectations. So the existence of normal conditional expectations is very tricky. And the very best result is Takasakis Theorem, which is very illuminating. So if you have a FNS weight, then there exists a weight-preserving normal conditional expectation. What does weight-preserving mean? I don't think I've defined it yet. It just means that W of E is equal to W. That's what weight-preserving means. Normal conditional expectation E from M to D, if and only if. So two conditions. First of all, W has to restrict to a semi-finite weight on D. And the second condition is the modular group, the Takasakis modular group of W leaves D invariant. So sigma T D, I'm sorry, sigma T omega D is contained in D. And then we know that there exists a conditional expectation under these two conditions. So we should expect to see such conditions in the sequel, even in the non-commutative function algebra case. Now, I'm not going to talk about the modular group. I don't want to bring in the technicalities of the modular group into this talk, but there are simpler settings where this disappears. So in many settings in this talk, this condition is going to be disappear. This condition will disappear or have a simpler version, which is much easier to understand in many interesting cases. And I think we have one of those immediately. So for example, if we know that W restricts to a trace on D, then this modular condition disappears. It is replaced by a centralized condition. What does the centralized condition mean? It means that omega of dx is omega of xd for x in M and d in D. So this The set of D for which this is true is called the centralizer. So this condition is saying that D is contained in the centralizer. So in our paper, we have several complementary results in the case that W is not faithful on all of M. So in our later setting of non-commutative function algebras and extensions of the containing von Neumann algebra, there's no guarantee that these extensions are going to be faithful on all of M, like in Takasakis theorem. So we need to prove some complementary results. And some of the results are also local in character. And what local means that you basically are doing everything modulo projections in D with finite weight. So for example, local W preserving would mean that omega is omega of E, not on the whole of M, but just on PMP for every projection, P and D, for every projection, omega finite projection. So we get, for example, local weight variance, but with the following flavor. This is, I haven't stated this in the local form because this is actually a state result, but we can get weight results where you have a local condition. If you have a normal state on a von Neumann algebra, so we're not assuming faithful, but it's faithful and tracial on the subalgebra D, then D is in the centralizer if and only if there's a unique normal conditional expectation that preserves omega. So here's a similar kind of result. I'm just going to flash up several results that from the paper. If you have a von Neumann subalgebra, in the case that D is semi-finite, which means that equivalently it has a faithful normal semi-finite trace, then having a normal conditional expectation is actually equivalent to having a weight with D in the centralizer, and there's a locally version of that. And perhaps I'll just skip over this for sake of time. We will see very similar results later. I don't think we need to spend time here, but in particular, this result indicates that you should expect to see centralizer conditions in the sequel because of this equivalence. Okay, so here is a result that matches the result that I put up in the classical probability setting, that normal conditional expectations correspond to weight functions. So this is the most general. We'll see some special cases of this in just a moment that are easier. So the nasty thing about this theorem is it's completely general, but it has this nasty modular condition, which as we've said is you can't get away without it because of Takasakis theorem. The bijective correspondences between normal conditional expectations which commute with the modular group. I won't define that, but I will say that the modular group is trivial in many of the cases that you are interested in. So in just a couple of slides, we'll do one of those cases. And so this commutation turns out is trivial in many situations of interest. So the weight functions are elements that are affiliated with the positive part of the centralizer. M nu is the centralizer, which are defined on an earlier slide very briefly. So this is affiliation in the sense of von Neumann algebras. These density elements commute with D in the sense of unbounded operators. And which satisfy ED of H equals 1. Now you have to explain what ED means when you're applying it to an affiliated operator. So it's we're really using the normal extension of ED to Hogerup's extended positive part. And then part C is shows that this is in correspondence with normal semi-finite weights on all of M, which commute with nu, and I've kind of hidden the property that it has to satisfy. We'll see simpler versions of this theorem where I don't need to hide this because it's prettier. And then with respect to these correspondences, we have these very nice formulae that, for example, H is the Radon-Nicodemus derivative of rho with respect to nu. The expectation is given, you can give it in terms of the weight function and this ED that comes from Takasakis theorem. This is the one that comes from Takasakis theorem. This is the nu preserving the probabilistic conditional expectation, if you like. And then also you have a nice formula for this extension rho in C. So you have to be a little bit careful here. This, for those of you who are familiar with non-commutative integration, you'll know that you can't be too naive about what this actually means. You need to actually define this in terms of certain limits, and similarly for the expression over there. Because of problems with unbounded operators, you actually have to define these things carefully in terms of certain limits. So the takeaway again is that again you can study all normal conditional expectations in terms of weight functions, and one fixed probabilistic or weight preserving conditional expectation, and like we saw in the purely probabilistic case, any such normal conditional expectation, assuming that it is faithful, it is a probabilistic conditional expectation for a certain measure, or in the non-commutative case for a certain weight, and that weight in retrospect is the composition of our original weight nu with the conditional expectation. Okay, so I said I would mention some special cases. So this is a special case where we don't need the we don't need the modular group in some places. So semi-finite D is contained. This is the case where the D is contained inside the centralizer, and I'm not going to mention A and B because these are just like they were before. The new formulation is C. So again, we get extensions to normal semi-finite weights. But the condition here is simpler, that it simply contains D in its centralizer. And I defined the centralizer earlier, but otherwise this theorem is the same. And we can get an even more simple version of this theorem in the case that of a faithful normal tracial state. So for a faithful normal tracial state, which may be the only case that you care about, this may be the only case that you care about, there's a bijective correspondence between normal conditional expectations, and we don't need to say anything. We don't need to add any conditions about modular groups. Densities in L1 of M which commute with D and satisfy ED of H equals 1. So no further conditions than that. And notice that here we're in the non-commutative L1 space. We don't have to talk about affiliation. And the next part is extensions of tau restricted to D to normal states on all of them having D in their centralizer. And again, we get the same formulae as before. So you could probably just ignore the previous 3 slides and just think about just focus on this one slide, which gives the picture and shows that it's perfectly generalizes the classical case of probabilistic measures that we started by discussing. Okay, so let's turn now to part 3. How are we doing for time? Let's see. I think we're doing okay.
We have about 20 minutes.
Okay, I think we are doing okay. Yeah, this is so strange because it's as I said earlier, I can't see you guys, so because of the device I'm using, I should have pulled up the meeting on another device. But okay, so I think we're fine. Non-commutative weak star representing measures. So now we are going to talk about merging the two fields that we saw in parts 1 and part 2. So part 1, we talked about the function theory briefly. Part 2, we talked about the von Neumann algebra case, and we're going to try to merge them. So a non-commutative function algebra is just an operator algebra, which is a subalgebra A of a C star algebra C. And in this talk, I'm going to assume that A is unital, contains the identity of C. And as we know, scalar valued functions in this case are usually not so useful. Just remind you of from part 1 of the Hoffmann-Rossi theorem about weak star continuous characters of weak star continuous positive state extensions. So let's look and see how to merge these theories in part 1 and part 2. So in part 1, we had this existence of a conditional expectation, but in this case in part 2 we had the existence of the conditional expectation under various conditions. In part 1 we had this character and this representing measure, let's call it phi, which we saw in the Hoffmann-Rossi theorem, and we're going to try to merge these pictures. So in this case, we're going to think of our theta to find a parallel between these pictures. We're going to think about the theta in the first picture as being like the identity map, but we have to now see how we can relate the complex numbers to D. Well, that's not hard. That's not hard. We just we just instead of thinking about the complex numbers alone, we just think about the continuous functions times the identity contained inside of A, contained inside of M. So this is our picture for non-commutative representing measures. We have this homomorphism, and we're going to find a conditional expectation extending it. In fact, the case when A is equal to D and theta is the identity is the case of von Neumann algebra conditional expectations. Whereas in the Hoffmann-Rossi theorem, our D is the continuous functions times 1. So this gives you a way to merge these two theories. There's something that I meant to say. Of course, D is a sub von Neumann algebra in both cases. Okay. So that's what I just said. So we have this inclusion. The setting is that we have an inclusion. D is contained in A is contained in M, where D and M are von Neumann algebras and A is a subalgebra of M. And we'll define a D character to be a unital contractive homomorphism. It turns out that it's automatically completely contractive, which is also a D bimodule map. I think it's equivalent to say that it's the identity on D, as we saw in the Overson example. So then the question arises: do non-commutative representing measures for D characters exist? And the surprising answer, this is quite surprising, is yes, they do. Under they may, in fact, exist under complete generality under natural conditions, but we haven't been able to prove it in complete generality. And I hope that one of the purposes I would like to talk about in this session is that hopefully somebody might get interested in this and may be able to prove this in complete generality. We are able to do it under fairly general conditions, and the conditions start to trend towards the same conditions that von Neumann algebra conditional expectations exist. And the boundary that we're able to get to seems to suggest some new directions in the study of von Neumann algebra conditional expectations. So I think that's a very interesting aspect too. Okay, so I said this is surprising. So why should this result be a little unbelievable? Why should you be skeptical? So if you look at the picture, all maps here are complete contractions, weak star continuous. And so in particular, you are obtaining a Hahn-Banach type extension theorem for weak star continuous contractive or positive maps. But it is well known that there is no such theorem. There's no such general Hahn-Banach theorem. And there's not even in the weak star continuous case, and there's not even any norm-continuous Hahn-Banach theorem unless D was injective, which we're not assuming. So you would be right to be skeptical about this result. There is some magic going on, and basically the magic that's in the guts is that ancient idea of Saracen in the commutative case that I did earlier. It's buried in the guts of this machine is the idea in that proof. That is the only proof that I went through in this talk. So let's talk about the proof of such theorems. So at least in the case where your weight is a state, it involves 3 stages. So in the first stage, we show that W of phi. What is phi? Phi is your map from A to D. Extends to a normal state on M. That's the first stage. In the second stage, we can show that the latter normal state has D in its centralizer by proving a lemma that you can average over the unitary group to get that. In the third stage, we use some technology for conditional expectations that we developed to prove our main result, that indeed such states with D in its centralizer, actually, this was basically the technology I was reviewing in part 2, that such states with D in its centralizer possess associated D-valued normal conditional expectations. Okay, so from the second stage, this averaging technique, you want to average a normal state to get a normal state with the additional property that D is in the centralizer. So this is contained in the following theorem, and I'm probably running a bit out of time, so I won't read the whole theorem. I guess this is recorded, but the theorem says that if you start with a faithful normal state W, and then we're going to basically average over the unitary group, and this average is going to take place in the norm closed convex hull of this set, which will contain a normal state extending the restriction of the state to D, but now D is in the centralizer. And in fact, there's a nice formula for this. There's an explicit formula using the unique W preserving conditional expectation onto D prime intersection M. And some conversations with Roger Smith and Meredith Kalantar were very helpful in us getting to this this result. Then perhaps I'll just put up both parts of this theorem. So let's just see what this says. Suppose you have these inclusions. M is a von Neumann algebra with a normal state nu, and this normal state is faithful on the subalgebra D, and D is in the centralizer of nu, and A is a subalgebra of M. And let phi be a homomorphism extending the identity map on D. I think this is equivalent to saying it's a D bimodule map, if I remember correctly. If we could assume that nu of phi extends to a normal state with D in its centralizer, then there is what you want. There is a conditional expectation. There's the conditional expectation you want. The second part says, assume that this extends to a normal state, but now we're not assuming that D is in its centralizer. Then, and this follows by the result that I had on the previous slide, by that averaging technique, you then can extend it to a normal state which does have D in its centralizer by this averaging technique. And so again, we have the the normal conditional expectation. So, okay, so this is what the final theorem looks like in one of its iterations. So most of my remaining slides are just the main theorem, but in various incarnations. So this is the finite von Neumann algebra case. What do I mean by finite? I mean that M has a faithful normal tracial state. So in this case, what the theorem says is that if you have a Weak-Star continuous D character, then there is a normal conditional expectation that extends it. So you do have a non-commutative representing measure in the sense of this talk. In the sense of this talk, I should have mentioned that there are many competing notions of non-commutative representing measures, but I'm using it in the sense that I defined earlier, which generalizes Arbison setting and which is useful for certain problems and probably not useful for other problems. But this is the setting of this talk. So yeah, so many of the remaining slides will look almost identical to this, but just in slightly different settings. So this is the case where M has a faithful normal tracial state. Okay, so what happens if you don't have a faithful normal tracial state? Well, then you get many other variants of this. So for example, if M is commutative, if M is commutative, you don't need the existence of a faithful normal tracial state. You have it in full generality. You can take any commutative von Neumann algebra, any Weak-Star closed subalgebra, any von Neumann subalgebra D, and any Weak-Star continuous D character. Then you have your representing measure from M to D extending phi. Another setting, if D is atomic, you need no more restrictions on M, and this was from a paper with Flores and Zimmer. So here M is completely general, but D is atomic. But we get the same existence, we get the same theorem, the existence of the Weak-Star continuous positive. There exists this Weak-Star continuous positive extension. So you have your Weak-Star continuous representing measure. The next theorem would be the same theorem, which again, I won't state, you must be getting bored, but now M is sigma finite and D is contained in the centralizer. So sigma finite, that for example covers all the cases. This is for example if M is separably represented on a Hilbert space. So the technical definition of sigma finite means that you have a faithful normal state. Sigma finite means you have a faithful normal state, or equivalently that you have a faithful state. So if you get beyond the proof even in the sigma finite case is quite technical, involving the technology of Hogarth LP spaces. Then in the general von Neumann algebra case, the completely general case, the results are not quite as beautiful. And open questions start to appear. In particular, we do not know if our result is true in full generality, but we get results like this. So, okay, so this is a in this case. I'm sorry. Oh, okay. Yeah. So this is not the completely general von Neumann algebra case, but this is a case where we've got rid of the setting of D contained in the centralizer. So this condition has gone in this theorem, and then we get that there exists a conditional expectation from M onto D extending phi. Which is what you want, and it's von Neumann. It's completely von Neumann algebraic. It uses Hogarth's reduction method, and Louis, my colleague Louis, is an expert on this on Hogarth's reduction method, and this this particular setting. So unfortunately, I guess the negative feature is that we do not know. We do not actually know. It should, but we do not know if this conditional expectation is normal in this generality. So when you use Hogarth's reduction method, you basically are using that local method I was talking about earlier. So you got these local projections of, I'm sorry, no, I think that comment belongs to the next theorem. But the same issue pertains. So this is my final theorem. This is the most general result we have. So M is an arbitrary von Neumann algebra, but it has a strictly semi-finite weight. So we have some condition, and then again we get a conditional expectation, but we don't know if it's normal. And this theorem uses the previous theorem. So these theorems should be considered as a pair. It uses the previous theorem. The previous theorem is quite lengthy. This one is not quite so lengthy because it uses the previous theorem. But again, we have problems putting together the local pieces to ensure that this conditional expectation on the whole of M is normal. On the local pieces, it's normal, but when you put it back together on M, we don't know if it is normal in full generality. So thank you for your attention, and the paper is on the archive and is about to appear. So I will stop sharing. I will stop sharing and relocate my camera.
All right, thank you very much. We have time for questions, comments. Yeah, so if you have a question, then just go ahead and pose the question. There is someone. Well, there is a question in the chat asking for slides, for a copy of the slides.
Certainly, yes. I'd be happy to do that. It might take me about 10 minutes though, so I don't quite know how to do that. Can I email them to you?
You can email it to any of the organizers, I guess, and we will simply send it to those who are interested.
Okay,
You can
sounds
send
good.
it to me, David. You can send it to me,
Okay.
and then I can distribute to whoever wants a copy.
Okay, thank you.
Thank you indeed.
Yeah, so in other words, it sounds like contact Javad if you would like a copy.
Sure.
Or email me too. You feel free to email me too.
Right. I don't see any.
So let me ask, if you have this result, then what do you do next? You get inner-outer factorization, or?
Yeah, so that's a good question. So whether you can, so we're proposing a setting for non-commutative function theory which is very similar to Ovison's subdiagonal algebra setting, where you have inner and outer factorization and all of these things. So continuing to develop non-commutative function theory in this particular setting, generalizing what you can do in Ovison's setting, I think that's a very interesting question. How much of that is possible? But we have a companion paper from about 3 years ago where we do a few things.
So what's special about Ovison's setting? The diagonal is commutative, or?
So the great thing about, well, the very strong condition in Ovison's setting is that, well, there are many ways to phrase it, but one way is that if you take the set of adjoints of your elements in your algebra and sum those together with the elements in the algebra, that is weak star dense in the von Neumann algebra. So it turns out that condition is equivalent to like 10 other wonderful conditions like inner and outer factorization, or a Berling theorem, or a Gleason-Whitney theorem. So many of the theorems in classical H infinity turn out to be equivalent in this setting and equivalent to Ovison's condition. But now I guess we are going beyond that. So the question is, what remains, or what vestiges of all those other theorems can you find in this setting?
Okay, thank you.
Other questions? If not, then let's thank our speaker again.
Thank you.
Thank you indeed.